Some MATLAB numerical simulations to investigate signal quantization and quantization noise. The first set of simulations uses a sinusoidal message signal illustrated in this top trace by the thin line illustrating the sinusoid, and a varying number of bits to quantize this message signal, starting with 1 bit, which would be 2 levels. Since the amplitude of the sinusoid is 1, the signal power in the message is 1/2 the amplitude squared. That's 0.5 watts. The bottom trace shows the error signal. This is the quantized signal minus the actual signal, and it shows it traced out as a function of time. We can find the power in this noise signal by squaring the signal and then finding the average value. And that's easily done numerically with MATLAB. And it turns out that the noise power is 0.11 watts and some change. Using those two values, we can take the signal power divided by the noise power, then log base 10 and multiply it by 10, and that results in a signal to noise ratio of about 6.4 decibels. I then increase the number of bits to 2 bits, which is 4 levels, and you can see the shape of the 4-level approximation to the sinusoid in the top trace. Again, the bottom trace shows the error message, and the signal to noise ratio is about 12.8 decibels. This continues the experiment for 3 bits per sample, which is 8 levels, and the signal to noise ratio about 19 decibels. 4 bits per sample gives 16 levels and a signal to noise ratio of 25 decibels. 5 bits per sample gives 32 levels and a signal to noise ratio of 31 decibels. 6 bits per sample gives 64 levels and a signal to noise ratio of 37 decibels. And you'll notice that with more levels, the noise signal is getting smaller and smaller. 7 bits per sample gives 128 levels and a signal to noise ratio of 44 decibels. And 8 bits per sample gives 256 levels and a signal to noise ratio of 49 decibels. And this is as many bits per sample as I used in this experiment. If you collect the information from the previous slides and plot them out on a single slide for quantization noise, across the bottom axis we have the number of bits per sample, 1, 2, 3, 4, 5, 6, and 7, and 8. Up the vertical axis is the corresponding signal to noise ratio. I use the equation that we discussed in the notes and also plot in the thin blue line the value for the signal to noise ratio that is given, that we get from the equation. My measured values from my MATLAB simulations are in the orange line, and you can see that they line up very closely, especially for a higher number of bits per sample. The difference at a small number of bits per sample, I'm going to attribute to inaccuracies in the numerical simulation. This continues with a similar experiment, except this time I'm staying with 8 bits. That's 256 levels. And I start with a sinusoid with an amplitude of 1 and a signal power of 0.5 watts, and then find the noise signal and the power in the noise signal, which again is, and the signal to noise ratio about 49.8 decibels. And now I'm going to decrease the amplitude of the sinusoid. Here is the sinusoid with an amplitude of 0.9, and you can see that the signal power has decreased, and the signal to noise ratio has also decreased a bit, indicating that this is of less quality than the quantized signal with a larger amplitude. And now we'll decrease again. This is an amplitude of 0.8. Signal power is 0.32 watts. Signal to noise ratio 48 decibels. Decreasing again. This is an amplitude of 0.7. The signal power is 0.245 watts. Signal to noise ratio 46.98. Here is the amplitude of 0.6. Signal power 0.18 watts. Signal to noise ratio about 46 decibels. Amplitude 0.5. Signal power 0.125 watts. Signal to noise ratio 43 decibels. Amplitude 0.4. Signal power 0.08 watts, signal to noise ratio about 42 decibels, and the amplitude 0.3, signal power 0.045 watts, signal to noise ratio 39.5 decibels. This is amplitude 0.2, signal power is 0.02 watts, signal to noise ratio 36 decibels. This is amplitude 0.1. Signal power is 0.005 watts. Signal to noise ratio is 30 decibels. And one more time, even smaller, this is an amplitude of 0.05. Signal power 0.00125. Signal to noise ratio 24 decibels. Again, collecting the information on the previous slides and showing them on a single graph, I've got the message power in watts across the bottom from when the amplitude was 0.05 volts. The power is very small, and the maximum when the amplitude is 1 volt, power is 0.5 watts. On the vertical axis is the signal to noise ratio in decibels. Again, I use the equation that we discussed in the notes to calculate the theoretical value. That's in the thin blue line. But you can see this, my measurements from my numerical experiments line up very closely. Again, I would attribute any difference at all to inaccuracies involved in the numerical simulation. The next experiment, again, uses 8 bits per sample, so we are at 256 levels. But this time I'm using a mu law compressor with the compression factor mu equal to 100. And if you look closely at the approximated sine wave as shown here, you can see that especially, let me lighten this up, especially here at the higher amplitudes. It didn't do it. There we go. Maybe that'll. At the higher amplitudes, you can see that the spacing between the levels is greater, and this is, you can see it down at this end as well. So with compression, we are using more narrow spacing for small values of the message signal, and a wider spacing for the higher values of the message signal. And in this way, we hope to improve the signal to noise ratio. So I ran a numerical experiment to determine if it does or not. This is an amplitude, and I'm going to now decrease the amplitude of the message signal and see how it changes the signal to noise ratio. Again, the amplitude is 1, signal rate power is 0.5 watts. And below is shown the error message, and you can tell that in the regions where the message signal is large, the error message is large, or the error signal, this would correspond to noise, is large. And in the regions where the message signal is small in magnitude, the error signal is also small in magnitude. but still it's easily done in MATLAB to square the signal, take the time average, and we determine here that the signal to noise ratio is about 39 decibels. Here the amplitude of the message signal is reduced to 0.9 volts, and the signal to noise ratio is 38.8 decibels. The signal amplitude dropped to 0.8 volts, signal to noise ratio 39.6 decibels, signal amplitude 0.7 volts, signal to noise ratio 39 decibels, signal amplitude 0.6 volts, signal to noise ratio 38.8 decibels, signal amplitude 0.5 volts, signal to noise ratio 38.7 decibels, signal amplitude 0.4 volts, signal to noise ratio 38.8 decibels, signal amplitude 0.3 volts, signal to noise ratio 38.9 decibels. Signal amplitude 0.2 volts, signal to noise ratio 39 decibels. Signal amplitude is 0.1 volts, signal to noise ratio 39 decibels. And here's the smallest signal. The amplitude is 0.05 volts, and the signal to noise ratio is about 38 decibels. I collected the information on the previous slides. Again, this is quantization noise, 8 bits per sample using mu law compression with a mu factor of 100. The message signal power across the bottom axis. Up the vertical axis is the signal to noise ratio. I use the equation discussed in the notes for calculating the signal to noise ratio with a mu law compressor, and that's the thin blue line that you can just barely see a bit of. And the orange line is the results I found from my numerical measurements. And again, you can see that it lines up very closely. The small differences, again, I'm going to attribute to inaccuracies that are built into the numerical process or the numerical calculation process. Here's a comparison of the quantization noise with 8 bits per sample for both uniform quantization and non-uniform quantization with a mu law compressor. The uniform quantization is shown in the orange line. This repeats the line that we saw on a previous slide. The non-uniform quantization with the mu law compressor is shown in the blue line, and you can see it's essentially a constant regardless of the message signal power. So as we previously discussed, there is an input message power range where the compression would be of an advantage and would improve the signal to noise ratio. That is more or less down here about lower than about 0.05 watts, which would correspond to an amplitude of let's see, about 0.3 volts on the message signal. So for low power messages, the compressor performs with a higher signal to noise ratio and thus a better quality signal. But for message power larger than about 0.05, the uncompressed, the uniform quantization performs with a higher signal to noise ratio, just as we discussed with the notes. Now I want to show some examples of noise induced by quantization of a signal. So for a baseline signal, this is a 440 hertz sine wave, the cleanest sine wave that I could generate. It's not a continuous signal even now. It is sampled at the CD sampling rate of 44,100 samples per second. but as a baseline, this will be the cleanest signal that I can get. And I can hear my dogs barking in the background as well. I'm not sure if you can or not, but let's listen to this tone. Another way to examine this signal is to look at its spectrum. I'm playing this audio signal in a program called Audacity, and it has the capability of doing a frequency analysis. And this is the frequency analysis. We can see that it has a peak component at 440 hertz, and it does not appear to have any significant harmonic components. Just as I start recording again, the dog starts barking again. This is the same 440 hertz sine wave that is being now quantized with 8 bits per sample. That's 256 levels, and the signal really doesn't appear any different. Let's see if it sounds different. I could hear a bit of a buzz in the signal, and if we look at the spectrum, as in addition to the peak at 440 hertz, there is a bit more of tiny little peaks at other frequencies as well. Although I'm not sure if you would call that significant yet. This is the 440 hertz sine wave with quantized with 7 samples per or 7 bits per sample. That's 128 levels, and this is what it sounds like. I could definitely hear clicks in the background of that. The spectrum of the signal is showing additional noise in the frequency analysis. You can see the little lines becoming more and more prominent. Those represent noise in the signal. This is quantized with 6 bits per sample. That's 64 levels, and you can quite clearly see the effect of the quantization on the signal in its time form. And this is what the quantized signal sounds like. And the noise is becoming annoying at this point. This is the spectrum of the signal, quantized with 64 levels, and you can see even more evidence of the noise in the spectrum. This is 5 bits per sample in 32 levels. And the corresponding spectrum. This is 4 bits per level. This is 4 bits per sample. This is 16 levels. And the noise is even more apparent in the spectrum of the signal. This is 3 bits per sample. This is 8 levels. And the corresponding spectrum. This is 2 bits per sample, 4 levels. And the accompanying spectrum. This is 1 bit per sample, 2 levels. And the spectrum of what is essentially a square wave. It's got a fundamental frequency of 440 hertz, and then it will have all of the odd harmonics. So that would be 3 times 440 is going to be 1318 hertz, and then 5 times 440 is going to be 2200 hertz, and etc. 7 and 9 and 11 and 13. So that's the odd harmonics that make up this square wave.